This lecture is the third in a 5-part series about EEG montages. In it, I will talk about common electrode reference montage. This talk will be conducted in a question and answer format. The first question is, in common electrode reference montage, input 2 of each amplifier comes from the same electrode. A true, B false. You would think that the answer to this question has a straightforward answer, but it does not. The term common electrode reference montage has been used to describe multiple arrangements. It is used when the same electrode is used at input 2 for all the differential amplifiers constituting a montage. I have represented this in this frame by using O1, and in this frame by using A1. At times, common electrode reference montage refers to connecting in the input 2 slot of all its differential amplifiers a combination of 2 electrodes as a single line. Here I have represented this possibility as bilateral ear connections, that is, as A1 and A2 being put together into one line and connecting it to all input 2 of all the amplifiers. But that is not all. The guidelines from the Academy of Clinical Neurophysiology also considers common electrode reference montage when an ipsilateral ear are used to connect each hemisphere. And the EEG Primer, 3rd revised edition, lists as common electrode reference montage a montage with an arrangement that includes 3 different reference electrodes coming through input 2. As you can see highlighted in this frame, A1 was used for the left hemisphere, A2 for the right hemisphere, and CC was also used for some of the left hemisphere electrodes. So the answer to this question is false. Next question. Common electrode reference montage can use cephalic or non-cephalic references. A true, B false. There are 2 types of common electrode reference montages: cephalic and non-cephalic. In the head, the common electrode can be placed in the mastoid, in the ear, in both ears, in the chin, in the forehead, or at the level of the scalp. In the body, the common electrode can be placed in the leg, in the anterior chest wall, and in the back of the neck. So the answer to this question is true. Next question. The most widely used non-cephalic reference is A. Neck ring reference, B. Neck chest reference, C. Right, left ear's reference, D, none of the above. All the locations mentioned in this question have one thing in common. They are constructed to decrease cardiac artifacts. The external notch to the back of the neck reference is apparently the most frequently reference used for this purpose. It seems to be the best arrangement to decrease the artifact created by the R wave of the EKG. The truth is that I have never seen it being used in pediatrics. So the answer to this question is B. Next question. The amplitude of a potential increases with inter-electrode distance up to about dash centimeters. A, 5, B, 6, C, 10, D, 20. The magic number is 10 centimeters. So the answer to this question is C. Next question. The analysis of the distribution of EG potentials acquired using common electrode reference montage can be represented by A. Voltage electrode position graph, B. An isopotential map, C. A polarity graph, D. All of the above. Potentials encountered while reviewing an EEG using common electrode reference montage, as the one highlighted in this frame, can be represented as an isopotential map, a voltage electrode position graph. Notice that the lines indicating the voltage arise from the position of the electrode and not from between the electrodes, as when representing this structure using bipolar montages. The third method that can be used to represent a common electrode reference montage is a polarity graph. So the answer to this question is D, all of the above. Next question. An electrical field has a maximal level referred to as maximum, a minimal level referred to as minimum, and intermediate levels. A true, B false. This frame depicts two independent three-dimensional electrical fields. The top one is a negative field. The bottom one is a positive field. Both have a maximum. The maximal negativity is the highest negative voltage of a negative field. The maximal positivity is the highest positive voltage of a positive field. In addition to maxima, each electrical field has a minimum. The minimum negativity is the lowest negative voltage represented in a negative field. The minimum positivity is the lowest positive voltage in a positive field. And in addition to maxima and minima, electrical fields have in-between or intermediate levels. Here I am representing in-between negativity for the negative field, and in this frame I am representing the same thing for the positive fields. So the answer to this question is true. Next question. The term uncontaminated common electrode reference montage refers to a common electrode reference recording performed using the maximum or the minimum of a field as the common electrode. A, true, B, false. In this frame, I have represented the maxima and the minima of a negative electrical field and of a positive electrical field. They are both independent, and if we assume a single radial dipole generator as the source of all the potentials recorded at one time by an EEG at the scalp, they cannot coincide in time. In this frame, I have represented the two fields. They are both independent at a time because we have assumed that a single radial dipole generator is the source of all the potentials being recorded at one point by the EEG. Hence, at one instant in time, all the potentials in a negative field will be more negative than its minimum. I have represented this by the aqua arrow. And at another instant in time, all the potentials of a negative field will be less negative than its maximum. And we can make the same comments regarding positive fields. At one instant in time, all the potentials of a positive field will be less positive than the maximum, while at another instant in time, all the potentials of a positive field will be more positive than its minimum. In any of the previously described situations, all the potentials will either be more than the minimum or less than the maxima, and all the wave created by these potentials will be expressed in the same direction, or they will be neutral. So the answer to this question is true. Next question. In this voltage graph, the reference represents A, the minimum positivity, B, maximal positivity, C, maximal negativity, D, minimal negativity. The figure, as you can see, represents a voltage graph. It has 4 levels represented by 4 yellow lines. The 0 dashed line represents the neutral point. The R, by virtue of it being on the positive side of the 0 line, corresponds to a positive value. And since the reference line is the closest to the neutral line, it is considered the minimal positivity. In this new frame, I have represented 4 electrodes by adding 4 dots of different colors at different voltage lines. The green dot represents the most anterior position by virtue of its proximity to the vertical double-headed arrow line, and it is also the minimal positivity since it is the electrode that is closest to the neutral line or the 0 line. The aqua dot represents the most posterior positioned electrode by virtue of its distance from the vertical line, and it also represents the maximal positivity since it is the furthest electrode from the zero line. Now I have added a corresponding isopotential map, and I have represented the waves that would be present if the potential from each of the electrodes would be measured in a bipolar fashion from an imaginary perfect neutral point, that is, from the zero line. Notice that the waves go down. They do so because they are positive. Now I have introduced in the isopotential map solid lines representing electrodes entering into input 1 and dashed lines representing electrodes entering into input 2 of a differential amplifier. Notice that the input 1 comes from the scalp, whereas in this case I am representing input 2 as a non-cephalic reference. This electrode is acting as the common reference electrode. I have now introduced a wave by the side of the reference electrode in the isopotential map. The polarity of the wave form, that is, the wave that is forming the common reference, is positive. It is positive because, as you can see at the polarity graph, the reference is on the positive side of the zero line. You should also notice that the amplitude is the lowest of all the wave represented in this frame. This is so because it is the one that is closest to the zero line in the voltage graph. Take a second to compare these waves, that is to compare this wave with the ones above. Thus the answer to this question is A. Next question. The reference represents A. minimal positivity, B. maximal positivity, C. maximal negativity, D. minimal negativity. In this question, as in the previous one, all the voltage lines are below the zero line, thus all are positive. The reference line is the most positive since it is the furthest line from the zero line. Thus, it represents the maximal positivity. In this frame, I have introduced an isopotential map representing the same field as in the voltage graph. And by the side of it, I have introduced the corresponding wave as if they were being measured from an electrode in the referred to an electrode in the zero line. Hence, the wave produced by the non-reference electrodes are of lower amplitude than the wave captured at the reference electrode. This is so, as you can see, because the reference is further from the zero line than the other electrodes. So the answer to this question is B. Next question. The reference in the voltage graph represents A. minimal positivity, B. maximal positivity, C. maximal negativity, D. minimal negativity. In this question, the position of the zero line has changed. Its new position makes all the yellow lines and the reference line negative. Since the reference line is the closest to the zero line, it represents the minimal negativity. So the answer to this question is D. Next question. In a common electrode reference montage, the absence of a phase reversal may indicate that A. The reference electrode is in the minimum. B. The reference electrode is in the maximum. C. The source of the field is a radial dipole. D. All of the above. If a tracing recorded using a common electrode referential montage has no phase reversal as the epoch in this frame, we can make two sound assumptions. One is that the reference electrode is either the maximum or the minimum of the electrical field for that given moment. So, in this case, and at the time indicated by the aqua arrow on the tracing, T7 is either the minimum negativity or T7 is a maximal positivity, since all the waves occurring at that time are either neutral or in the same direction. The second sound assumption that can be made is that the generator of the activity is a radial dipole, rendering only one of its pole amiable to the EEG recording. So the answer to this question is all of the above. Next question. O1 is A. Minimal positivity. B. Maximal positivity. C. Maximal negativity. D. Minimal negativity. The first figure in this frame is an isopotential map with 5 scalp electrodes. The one labeled R is the reference. The green, yellow, magenta, and aqua electrodes are connected to the input 1 of one differential amplifier, and the reference electrode is connected to the input 2 of all the differential amplifiers. In this frame, I am introducing a polarity graph. I will explain it again to make sure we are in the same page. The vertical line, the double-headed arrow by the side of the microvolt abbreviation, has a negative sign at the top and a positive sign at the bottom. It indicates polarity. The yellow lines represent voltage levels, one for each of the non-referential electrodes. I have now added a cartoonish representation of the wave in question. Notice that their amplitude transition between them is smooth. These waves represent the electroencephalographic element highlighted in the tracing in the question. I like to stress that this pattern is one of the two major categories encountered during reviewing common electrode reference montage. This pattern is called the no phase reversal pattern. This pattern, when encountered while reviewing an EEG using a common electrode reference montage indicates that the reference electrode is either at the minimum or at the maximum of the electrical field, as we have previously mentioned. Although I hate to remind you at this point because it makes our explanation a little bit more confusing, I nevertheless will remind you that we are basing that the reference electrode is either the minimum or the maximum on two assumptions. These assumptions are, as we previously mentioned, sound because most of the time they are correct based on experience. The first assumption is that we are capturing all the electrical fields present, or that is the electrical field present at the scalp at the point in time the electrical element is being captured. And the second assumption is that the whole head is involved by a single field. So when encountering this pattern, that is, when encountering no phase reversal in a common electrode reference montage, the next question should be whether we are dealing with a reference being at the maximum or at the minimum. Also, judging by the absence of phase reversal and the smooth amplitude transitions between adjacent wave, we have to answer whether we are dealing with a polar field, either frontal or occipital, that is smoothly spreading in the opposite direction. And finally, we need to consider if the field is either positive or negative. I hope that by looking at this diagram, this concept becomes clear to you. In the next frame, I am going to represent each of these possibilities as diagrams. To make this clear, I have given each of these possibilities a number in this frame, as you can see, going from 1 to 8. Possibility 1 and 2 represent positive and negative frontopolar fields with the reference being at the minimum. Possibilities 3 and 4 represent positive and negative occipitopolar fields with the reference being at the minimum too. Possibilities 5 and 6 represent positive and negative frontopolar fields with reference being at the maximum. Possibilities 7 and 8 represent positive and negative occipitopolar fields with the reference being at the maximum. So here, I would like for you to answer this question. I think that you will answer it, that your answer will be yes. And I am sure that you have already figured out not only the location of the generator, but also the polarity of the generator. Nevertheless, I will go through the logical process that it takes to get to the answer, because it is a good exercise to apply in a situation where the origin of the wave is well known, in order for us to apply it in those cases where the origin of the wave is not known. These possibilities can be considered by asking ourselves specific questions. Regarding the first possibility, we can ask ourselves, are we dealing with a frontopolar positive field and a minimal positive reference? Here, I am representing a positive frontopolar field being monitored by a common electrode reference montage with the reference located at the minimal positivity. Now, I am introducing the corresponding voltage graph. Notice that the reference is at the minimum positivity since it is the closest line to the zero line, and that all the other electrodes are positive in relation to the zero line, and that the color of the electrodes in the voltage graph and the isopotential map are matched, the green being the most positive and most anterior. In this frame, I have added the cartoonish representation of the wave in question. I have represented them in gray because I will introduce on top of them the product of the different fields as captured by the existing montage. This will become clear in a few seconds, I hope. In this frame, I have introduced the waves as they would appear if the non-reference electrodes could be connected to a neutral electrode, that is, as if they were being collected from an electrode in the zero line. This connection is not represented in this frame. As you can see, the green wave is the largest. And the reference wave is the smallest. This is so by virtue of their distance from the zero line. Now I will introduce a blue box to explain what happens within the differential amplifier. This blue box is there to show you what happens in each amplifier, as I previously told you. So inside the amplifier, certain things happen in order to produce a wave of a given amplitude and polarity. That is, in this blue box, I will show what happens when we connect the non-reference electrodes to the differential amplifier input 1 and the common reference electrode to input 2 of the differential amplifiers. I'd like to refer your attention to the reference electrode at the isotope map. In this frame, I am representing in the blue box the brown wave, that is the reference wave. I am representing this wave with an opposite polarity from the one present in the proximity of the isopotential map. I have done this to indicate what happens when the wave reaches input 2 of the differential amplifier. As you know, the wave will be inverted. Next, I take the green wave and place it in the box, but with the same direction as it was presented by the side of the isopotential map. I have not changed the polarity of the wave because it is entering through input 1. Thus, its polarity is not inverted. As you know, the function of the differential amplifier in this case is to subtract the amplitude of the common reference, that is, the brown wave, from the amplitude of the wave coming through input 1, that is, the green wave. The result of this operation is a wave with a certain amplitude as indicated by the arrow, which coincides with the amplitude in question arising from the first derivation. The second wave is produced by the same mechanism, and as you can see, it coincides with the wave from the second derivation. So is the third and the fourth wave. The gradual reduction in amplitude as the distance from the source increases is the consequence of three factors: the amplifier flip function, the amplitude of the wave generated under the non-reference scalp electrodes, and the amplitude of the wave arising from the reference electrode. So, looking at the chart with all the options, we can say that option 1 is a sound possibility. Next, we need to ask ourselves whether the second option is a sound option or it is not. In this frame, I have introduced the appropriate isopotential map with its corresponding waves, and by the side in gray, the cartoonish representation of the waves in question. Now I have introduced the voltage graph corresponding with the isopotential map. Notice that all the electrodes represented in the voltage graph are on the negative side of the graph. So all the multicolor waves are up. Also notice that the reference is the closest to the zero line, also on the negative side. So it will be the smallest wave. As you can see in this frame, I have omitted many steps and just shown you that the first wave produced by the mechanism we previously detailed will correspond to what you are seeing in this frame. The bottom line is that the wave produced by such a configuration is in the opposite direction than the wave in question. So option 2 is not a sound option. Next, we should analyze option 3. In this frame, I am representing the corresponding isopotential map, the corresponding wave, and in gray by the side, the waves in question. Now I have added the corresponding voltage graph. And in this frame, I have introduced the blue square and the waves that will result from the function of the differential amplifier. So option 3 is not a sound option. Next, we should consider option 4. In option 4, we are dealing with an occipital polar negative field being referred to a minimal negativity represented in the scalp at the time of the recording. This frame represents an isopotential map corresponding to option 4 and the waves in question. Now I have added the corresponding voltage graph. And in this frame, the waves are being placed in the blue box to represent what happens at the level of the differential amplifier. In addition, as you can see, the arrow points to the result of this arrangement. which, as you can see, does not correspond with the waveform from the first derivation of the waves in question. Hence, option 4 is not a sound option. Now we must consider option 5. In this case, we're dealing with a frontopolar positive field reference to the maximum positivity. This frame represents the frontopolar positive field in an isopotential map and the maximal positive reference. The gray waves, as in the previous frames, indicates the waves in question. I have introduced the blue box and the corresponding wave after the activity that takes place in the differential amplifier. As you can see, the wave doesn't correspond with the one in question arising from the first derivation. So option 5 is not a sound option. Now we must consider option 6. Option 6 consists of a frontopolar negative field being referred to a maximal negativity. This frame represents the frontopolar negative field and the maximal negativity at the reference view in an isopotential map. The gray waves, as you know, represent the waves in question. By doing the same operation as we have done previously, you can see that the resulting wave from the first derivation is smaller than the one in question from the same derivation, and that the following waves using the same process are bigger and not smaller as the ones in question. This process continues in the further you go from the source, the bigger the wave will become. And this can clearly be noticed in the fourth derivation. So option 6 is also not a sound option. Next, we must consider option 7. Option 7 consists of a maximal positive occipital polar field referred to a maximal positivity. This frame represents the isopotential map and the wave corresponding to option 7 and the wave in question. In this frame, I have added the corresponding polarity graph. Remember that the polarity graph is represented as if all electrodes are being viewed from the zero line. In this option, we are considering a positive field since all the electrodes are on the positive side of the zero line, and the reference electrode as the maximal positivity because it is the furthest from the zero line. As you see, the reference is the biggest wave since it is, as I previously mentioned, the further from the zero line. Being that the activity going into the differential amplifier through input 2 gets inverted, and that this activity is maximal it stands to reason that the polarity coming out of the differential amplifier will be ruled by the amplitude of the wave from the reference. Then, when we bring the green wave into the differential amplifier box, the product, as expected, is a negative wave. This is not consistent with the wave in question arising from the first derivation. Hence, option 7 is not a sound option. Next, we must consider option 8. Option 8 consists of an occipital polar negative field referred to a maximal negativity. This frame contains the voltage graph and the isopotential map representing option 8. So, inverting the reference wave and subtracting from it the green wave yields a wave that matches the wave of the first derivation of the wave in question. We can then repeat the same operation for the yellow wave, the magnetar wave, and the aqua wave. And as you can see, they all coincide with the amplitude of the waves in question. So option 8 is a sound option. So we go back to the tracing in question and conclude that either we are dealing with a frontopolar positive field being recorded from a reference electrode corresponding to its minimum, or we are dealing with a posterior negative field, that is a posterior polar negative field being recorded from a reference electrode corresponding to the maximum of the field. The choice in this case is easy, since I think that from the very beginning you recognize this activity for what it is, eye movement. Yet, from the point of view of sequential thinking and thinking process, it is important that we remember all the assumptions to which we have alluded to. So the answer to this question is A. Next question. In a common electrode reference montage, the presence of a phase reversal indicates that A. The source is a radially oriented dipole and the reference is nor the maximum or the minimum. B. The source is a horizontal dipole and the reference is neutral or in between the minima of each of the fields. And C. A and B. This tracing demonstrates a phase reversal. When faced with a phase reversal in a common electrode reference montage, the phase reversal indicates one of two things. We are either dealing with a radial dipole with only one pole visible to the electrode, recorded from a contaminated reference, in other words, from a reference electrode that is neither the minimum nor the maximum of the field. This frame, which includes a voltage graph and an isopotential map, depicts this possibility. As you can see in this frame, I have represented an isopotential map corresponding to a radially oriented dipole producing a single positive generator at the scalp. The phase reversal in this situation occurs because the reference electrode is neither at the minimum or at the maximum voltage of the field. Notice in the voltage graph the position of the non-reference electrodes in relation to each other, in relation to the zero line, and in relation to the reference electrode. The other possibility is that we may be dealing with a horizontal dipole view from a non-contaminated source. So in this case, the common reference electrode is either neutral, or at least it is between the minimal potential of each opposite polarity fields. I will give you an example with the hope that it will become clearer. In this frame, you can see an isopotential map. This map shows two fields produced by a horizontal dipole with expression in the scalp. And you can also see in this frame its corresponding waves. Please notice the phase reversal between the yellow and the magenta electrodes. The reference electrode is at a neutral voltage, neither negative or positive, or at least it is at a voltage that is less positive than the voltage of the blue electrode and less negative than the voltage of the green electrode. On top of this frame, I am introducing the corresponding voltage graph. Notice that the zero line and the reference line are at the same location in the middle of the voltage graph. As you can see, the isopotential map will not significantly change as long as the common reference is, as in this frame, slightly more positive, but not more positive than the least positive non-referential electrode, or slightly negative as long as it is not more negative than the least negative of the non-referential electrodes. So the answer to this question is C. Next question. The most frequent cause of phase reversal in common electrode reference montage is a horizontal dipole. A true, B false. This voltage graph depicted in this frame shows a negative field. Notice that the yellow lines are all above the zero line in the negative side of the chart. The yellow lines correspond to the different voltage levels, as we have previously explained. Also notice that the four electrodes are represented by dots as they had been in the past. They are at different voltage levels, as you can see. Now I am introducing time, in this case time 1. At time 1, were we to view the activity presented in the voltage graph using a bipolar montage, we would see a phase reversal at the yellow electrode. It would be so because the yellow electrode is at the highest voltage level. The phase reversal, as you know, will be called an instrumental phase reversal. Now, I need you to assume that the field recorded at the scalp level is held constant over time. I have to express the passage of time, or I will express the passage of time by adding the letter T followed by a progressively larger number. As you can see, assuming, as we previously stated, that the scalp field is held constant over time, the bipolar montage recording characteristics will not change. Now, were we to change the montage to a common electrode reference montage and assume that the potential captured during this recording is the same as the potentials captured during the bipolar montage, we will see something quite different. The tracing collected in such circumstances will, unlike the bipolar recording, change over time. Let us imagine that the value of the reference electrode at time 1 is close to the zero line, representing the minimal negativity in the field. We would get no phase reversal in such conditions. Were we to change the reference electrode so that at time 2 it be at a more negative value, we would then get a phase reversal because some of the non-referential electrodes would be more negative and others would be more positive than the reference electrode. But in addition, the potentials recorded at both ends have the same polarity. That is a polarity different from those in the middle electrodes. Were we now to move the reference to be at a slightly more negative value as indicated by the arrow, we would still get a phase reversal because the yellow electrode is still more negative than the reference, while the other electrodes are more positive than the reference. Finally, were we to move the common reference electrode at an even more negative value, that is, more negative than any other of the non-reference electrodes, no phase reversal will occur since the common reference electrode is now the most negative of all the electrodes. The situation we have just described with the reference electrode not at the maximum or the minimum is, as we already know, called a contamination source or a contaminated source. This situation is by far a more frequent cause of phase reversal in common electrode reference montage recording than a true horizontal dipole. This situation, that is the presence of a contaminated reference, can occur with a field with its maximal amplitude in the middle flanked by lower amplitudes, can occur in the presence of a field with its maximal amplitude in the posterior polar region, or a field with its maximal amplitude in the anterior polar region. So the answer to this question is false. Next question. Which situation while looking at a common electrode reference montage should make us think that we're dealing with a phase reversal produced by a horizontal dipole? A. Eye movements. B. A setting consistent with benign Rolandic epilepsy. C. An unexpected large voltage difference between two adjacent electrodes. D. All of the above. A horizontal dipole should be considered when the characteristic of a pattern of waves suggests one of the following conditions. eye movements, epileptic discharge after epileptic surgery, that is spikes through skull defects, benign focal epileptic discharges of childhood, that is benign Rolandic epilepsy discharges, small sharp transients of sleep, EKG, and when an unexpected large voltage difference is present between two adjacent electrodes. I will explain the later situation in the next few frames. In this frame, I have represented the same figure I presented to you a few minutes back to indicate the voltage graph pattern produced by a horizontal dipole and the isopotential map representation of a horizontal dipole. In this case, I want you to notice the voltage difference between the green and the yellow electrodes. Which I am representing by a light purple arrow between the green and the yellow electrodes. And between the magenta and the aqua electrodes, which I am also representing by a light purple line. Now notice that the one between the yellow and the magenta is much larger. Such a situation suggests that a phase reversal present in a common electromontage is due to a horizontal dipole. So the answer to this question is all of the above. Next question. A true phase reversal, one produced by a polarity reversal, will produce a double phase reversal in bipolar recording and a double phase reversal in reference recording. True or false? This frame, as you can see, shows a voltage graph. Two electrodes, the green and the yellow electrodes, are above the zero line. Those are negative. The magenta and the blue electrodes are below the zero line. Those are positive. The reference is in the zero line, thus it is neutral and can be considered the minima of the positive and negative coexisting fields. I have included in this frame the isopotential map corresponding to the voltage graph. Were we to record this isopotential map using a bipolar recording, we would get a double phase reversal. On the other hand, were we to look at the same isopotential map using a referential, that is a common electroreferential montage, we would get a single phase reversal. As you can see, this phase reversal will have a large voltage gradient gap between the yellow and the magenta electrodes. So the answer to this question is false. Next question. An instrumental phase reversal, one not produced by a polarity reversal, will produce a phase reversal in a bipolar recording, but no phase reversal in a reference recording if the reference is uncontaminated. A true, B false. This voltage graph depicts a negative field with maximum at the yellow electrode. The reference again is the neutral point, thus at the minimum of the field. On the left side, you can see an isopotential map depicting the electrode arrangement and the field corresponding to the voltage graph. You can also see that a bipolar arrangement of the electrodes have been placed in with their corresponding wave pattern. The arrow in this frame is pointing to the waves that are color matched with the electrodes. These waves represent how they would appear if recorded from a fictitious neutral point. Notice the high amplitude of the yellow wave, the small amplitude of the aqua wave, and that the green and the magenta waves are at the same level. Now I have introduced the same potential but using common electrode reference montage to evaluate them. In this case, I have placed the reference at a neutral point. Notice that the wave from the fictitious neutral point have not changed. When compared with the one previously shown, that is so because both are collected from the same fictitious neutral point. Also notice that the waves pointed by the arrow are the same as those recorded using a fictitious neutral reference. The point is that if we choose a neutral point, the referential montage will yield information that is closer to the actual reality that we would get if we were able to record from a real neutral point. That is, it will allow us to see the wave as most likely they will be perceived in reality. So the answer to this question is true. Next question. In common electrode reference montage, if all channels show about the same amplitude and polarity, the activity is likely to arise from the reference electrode. A true, B false. As you can see in this frame, if all channels in a common electrode reference montage have the same polarity and about the same amplitude, the likelihood is that the activity driving such changes arises from the common reference electrode. It is far less likely that the waves would arise from a wide scalp field as it is represented in this frame. So the answer to this question is true. Next question. When using a common electrode reference montage, the presence of a white phase reversal indicates that the reference electrode is at the same voltage level than at least one of the scalp electrodes. A true, B false. This frame depicts a white phase reversal due to a horizontal dipole. The white phase reversal occurs because the reference electrode and one of the non-reference electrodes share one voltage level at the middle of the run. Hence, that electrode has no voltage output, which will translate into a flat line. This new frame depicts a narrow phase reversal. Usually, this type of reversal is just referred to as a phase reversal. A narrow phase reversal occurs when the field created by a horizontal dipole does not involve the reference. So the answer to this question is true. Next question. Common reference electrode montage obscure low to medium amplitude highly localized waves. A true, B false. This frame highlights a bipolar montage with a medium amplitude spike arising from F3. This spike is clearly seen using bipolar montage, and each spike has the same size because the distance between FP1 and F3 and between F3 and C3 is the same. The activity before the spike has a wider distribution. It is present from FP1 all the way to O1. Changing to a common electrode reference montage emphasizes the widely distributed activity just mentioned. Notice that the amplitude of the wave generated from P3 to O1 is about the same. This activity is now better seen from C3, F3, and FP1 because of the longer distance. Yet the waves generated from P3 to O1 using common electrode reference montage and bipolar montage has not changed. Also notice that the activity restricted to F3 in the bipolar montage is still restricted to F3 in the referential montage, but it is less well appreciated. I have included in the square the bipolar representation of the same activity so you can compare them. So closely placed electrodes behave like a spatial high-pass filter, emphasizing fast waves that involve one electrode. Widely spaced electrodes, as we encounter when using common electrode reference montage because of the longer inter-electrode distance, most of the time behave like spatial low-pass filters. They de-emphasize waves that arise from one electrode and emphasize waves arising from many electrodes. It happens that the spikes usually arise from one electrode, whereas a slow wave usually have a more widely distributed field. So the answer to this question is true. Next question. Common electrode reference montage behave like a spatial low-pass filter, whereas bipolar montage behave like a spatial high-pass filters. True or false? The spatial low-pass filter effect is a consequence of a wide separation between electrodes attached to the same differential amplifier. They remove or minimize highly localized wave, usually fast waves, and emphasize widely distributed wave, usually slow waves. This is what we typically achieve when we use common electrode reference montage. Spatial high-frequency pass filters result from placing electrodes close to each other. In an adult, the electrodes can be placed as close as 2.8 centimeters from each other and still get quite relevant information. Electrodes close to each other emphasize highly localized waves and remove widely distributed waves. Bipolar montage with closely placed electrodes behave like spatial high-pass filters. So the answer to this question is true. New question. The following comments are true regarding common electrode reference montage except A. Localization of the maximal potential is recognized by amplitude. B. Does not remove widespread potentials with similar amplitude and phase. C. Obscure low to medium amplitude highly localized wave. D. Localization of the maximal potential is recognized by phase reversal. Common electrode reference montage uses the same electrodes in input 2 for a set of amplifiers. Amplitude can be used for localization among the same set of derivations connected to the same input 2 of the differential amplifiers. Common electrode reference montage do not remove widespread fields. They obscure low to medium amplitude highly localized waves. In common electrode reference montage, the localization of the maximal potential is recognized by amplitude. So the answer to this question is D. Next question. When using a common electrode montage, the presence of a wide phase reversal should prompt you to change the location of the common electrode. A. True. B. False. A wide phase reversal implies an equipotential derivation recording sandwich between two conveying or diverting waves. The equipotential recording is created by the common electrode reference and one non-referential scalp electrode sharing the same voltage level. A wide phase reversal may occur in the presence of a horizontal scalp dipole, but more often they occur as a consequence or as an expression of a common reference electrode sharing the same potential level with a non-referential scalp electrode. So, in cases that you are not considering one of the situations listed in this frame, the best you can do is to change the position of the common reference electrode when you encounter a wide phase reversal. The effect of changing position of the reference electrode will be illustrated to you in this frame and in the following frames. In the current frame, this is just the same illustration that I had shown you before. As you can see, in this case, there is a true phase reversal, whereas in this case, there is a contaminated source. In this new frame, I have changed the position of the common reference electrode. I have done this to show you the effect on a true phase reversal, which is that the phase reversal will persist, contrary to what happens if the reference is contaminated, in which the phase reversal will disappear. The problem is that this is contingent in you changing the reference electrode to the right place, that is, to a neutral place. So the answer to this question is true. Next question. Which of the following montage best displays unilateral temporal lobe activity during stage 2 sleep? A. Ipsilateral ear reference montage. B. Link ear reference montage. C. Vertex reference montage. D. Contralateral ear reference. The decision to use one electrode as the common reference electrode hinges on many factors and on personal preference. But there are some commonly accepted rules that help decide where to place the common reference electrode. I will list these rules in the following frames. Number 1, place reference as far as possible from the region of interest. Not everyone agree with this rule, but as a whole, it works most of the time. 2, do not use the electrode with activity of interest as the reference if it can be helped. Again, most people believe that this should be the case, although some disagree. 3, do not use a reference at the location expected to be active during sleep. Do not use CC because vertex waves and K-complex arise from there. 4, if using a contaminated reference electrode, dilute it, but never interconnect ears. Again, not all agree. So as you can see, this rule seems to be made to be broken, but still, they are usually used as guides as to how to select a common reference electrode. So the answer to this question is D. Next question. An ear reference would be more suitable than a CC placement in all of the following situations except A. During a sleep recording. B. When temporal epilepsy is suspected. C. When sleep pathology is suspected. D. In the delineation of a frontal focus. In this tracing, you have a wide phase reversal involving F8, T4, and T6. It is important to stress that the most important finding in a bipolar montage is phase reversal. The same pattern is present a few seconds after. It is important to notice that at the same time, other waveforms triggered by the same or at least a temporally linked process is manifested itself at different electrodes, especially as a spike and wave at the T4 and C4 recordings. If we change the bipolar montage to one with both ears combined as a common reference, as we have done in this frame, you can see that a sharp activity now is present contaminating the reference electrodes, and it appears all over. Changing the reference to CC shows that the field of the spike is maximal at F8 and T4, suggesting temporal lobe epilepsy. So the answer to this question is B. Next question. Which of the following is not likely to be a consequence of combining both ears as a reference? A. An increase in heart artifacts. B. a predominance of the activity from ear with highest impedance. C. Detection of a temporal lobe asymmetry. D. Bilateral spread of unilateral temporal spikes. This frame summarizes the good and the bad about combining ear electrodes. Combining ear electrodes decrease hard artifacts. This is good. The activity from the ear with less impedance will predominate. This is a source of confusion. Temporal lobe asymmetry will not be detected. This is bad. And unilateral spikes will look bilateral. This is also bad. So the answer to this question is B. Next question. Which electrode should be avoided as a common reference when considering a sharp wave during a stage 2 sleep epoch? A. D4, B. C3, C. F7, D. F10. The classic activity during stage 2 sleep are spindles, key complexes, and vertex waves. This activity will contaminate a central common reference electrode and make analysis of the waveform difficult. So the answer to this question is B. Next question. Which electrode should be avoided as a common reference when considering if a run of sharp waves is real or artifactual during the review of a REM sleep epoch? A. T4, B. O2, C. O2, D. O1. This epoch shows temporal sawtooth sharp waves during REM sleep. They are more prominent in the central region than in the frontal and in the occipital regions. So the answer to this question is T4, A. Next question. Which electrode should be avoided as the common reference when considering whether a patient is in deep sleep or in coma? A. F3, B. C3, C. O2, D. F10. As you can see in this frame, the amount of slow activity in the frontal lobes is more prominent than the activity in the occipital lobe during stage 3 sleep. Hence, during coma, the amount of slow wave activity should be judged over the occipital and central regions more reliably than in the frontal region. So the answer to this question is A. Please take your time to answer the following questions. If you get them right, it means that you understand common electrode reference montage. I suggest you take a pencil and try to answer them on paper before you choose an answer. The epoch above belongs to which cartoon below? This frame shows a voltage graph and an isopotential map. As dictated by the scalp fields in the isopotential map, we're dealing with a field that is positive in relation to the reference. Now look at the voltage graph. Notice that all electrodes are below the zero line in the positive side of the vertical arrow representing voltage. The yellow, magenta, and aqua electrodes are in the same positive voltage line. Hence, their wave will have the same configuration. The green electrode is at the less positive level. So the answer to this question is B. Next question. The epoch above belongs to which of the cartoons below? As dictated by the scalp field in the question, the prevailing activity will be negative, and as such, it will be shorter above the zero line in the voltage graph. The yellow electrode is the most negative because it is the furthest from the zero line. The green and magenta electrodes are at the same voltage level. The aqua electrode and the reference electrode are out of the field, thus considered equal. So the answer to this question is A. The epoch above belongs to which cartoon below? Here, the reference is positive in relation to the scalp electrodes. In other words, all the scalp electrodes are negative, and since they are not involved by a field, they are considered to be at the same level. Notice that we are not taking distance from the reference electrode to determine magnitude of polarity. If we were, then the green and the aqua electrodes would be most negative. So the answer to this question is C. Next question. The epoch above belongs to which cartoon below? Notice that the yellow electrode is at the same voltage level than the reference electrode. So the answer to this question will be A. Next question. The epoch above belongs to which of the cartoons below? This frame shows the voltage graph and isopotential map of a positive field involving the last electrode and the reference electrode. A similar waveform pattern can be produced by a negative field that involves the three anterior-most electrodes equally. That is, all three electrodes being in the same voltage zone. Notice that despite the similitude between the wave, the isopotential map, and the voltage graph for each of these fields are very different. Notice that what has changed in the potential graphs is the position of the O line. So the answer to this question is C. Next question. The epoch above belongs to which cartoon below? This frame shows the voltage graph and isopotential map of a large negative field that involves the yellow electrode more than any other and the aqua electrode the least. So the answer to this question is B. Next question. The epoch above belongs to which cartoon below? This frame shows the voltage graph and isopotential map of a very restricted negative middle of the run field. So the answer to this question is A. The last few words regarding common electrode reference montage will be to summarize the good and the bad about it. Common electrode reference montage is good for the following reasons. It is excellent for detection of widely spread currents. It is excellent for analyzing artifacts, especially electrode artifacts. It is good to detect asymmetry and is also good because frequency is little distorted in comparison to how much it is distorted with bipolar montage. It is also good because it is able to detect deeply localized potential sources producing relatively flat gradients. On the other hand, common electrode reference montage is bad because phase reversal may be real or due to a contaminated reference, because they have a poor track record for source localization, because in cases of active reference, interpretations of the findings are very uncertain, because gains are lower than with bipolar montage. Therefore, sharp localized potential with the steep gradients may be missed. And also because voltage fluctuations at the reference electrode produces large voltage fluctuations in all derivations. Thank you.